Hello community! We have some brand new AI research that tells us reinforcement learning? No, we have something much better. We have the intelligence of a multi-agent system. So let's have a look. So we have here our little LLM and then we have 5 modules. Perception, memory, collaboration, reason, execution. And yes, we will apply this today here in a multi-agent system and we will put our agent on wheels. Yes, this is our use case. So let's have a look. First module, let's just go through and explain what they do. The perception model, it's easy. It interprets here the sensor data from the cameras, from radar, LiDAR sensors, whatever. It transforms the data into a textual description that the LLM can understand and reason about. And you say, oh, that's different. Memory. Now, easy. We have not only the internal memory, but we have now a memory we can share between our agents. And this external memory, if you want, will able to incorporate here past learning sessions here to help us with new decisions, or maybe the environment and the situation has only been handled before. The third one is the collaboration module. This is easier. It has here the communication capabilities and it negotiates here with other agents. It can generate strategies and propose them to other agents. So here we have the communication and collaboration happening. Plus the reasoning. This is now interpreting the collaborative strategy formed in a collaboration module and converts them into specific driving plans for each agent. It breaks down in the real action that the system is going to take. So, and then the reason engine is, of course, our core decision-making unit for each agent. And then simply, we have the execution model. But wait a minute, there is something beautiful, now something different. We do not go for an AI model. We go for a different one. I will explain this in about 4 to 5 minutes, but let's say we go with an intelligent driver module to give us here more control on the low-level controls for the vehicle, because we want to increase here the safety, the reliability, and the stability of our decision-making. So here you have it. All this together is now our new AI agent, plus, as I told you, a rule-based control system for numerical values in particular, and we're gonna have a look at this. As I told you, we have now a real-world case because we put our agents on 4 wheels. Plus, we have a new idea. So for my green grasshoppers, it is easy. You can go from perception to collaboration, from collaboration to reasoning, from reasoning to execution, and from memory to feedback loop, and you have more or less a self-learning system. So easy. This car just has to be on the road to learn to drive. Beautiful. Now, there is a new perspective that made me interested because I've chosen this particular new research paper for a reason. Now, you know, today, if we have a self-driving car, let's say this is here the blue one in the middle, we have an egocentric view. The car has all the radar, camera, LiDAR, whatever sensor. So the car is scanning its immediate environment and decide on the action to take next given its goal where it wants to go. So imagine now if multiple cars have an AI agent, because they are now autonomous and they can communicate, suddenly we have a flow-centric view. Now it gets interesting, because if all of those are agent and just accidentally, you remember my last video was about here the perfect communication protocol, if we have a multi-agent configuration, which has a dynamic structure, what a coincidence. Now we can use this knowledge and have here an interesting dynamic environment, because the configuration of the cars, let's say in the direct vicinity of our blue car, will change constantly if we are on a highway or somewhere in the city. So this is quite a challenge for the latest AI system. So let's have a look at a new solution. What we find, and this is the beauty, I think, that this paper does not focus here on the idea, yeah, we have a controlled environment and everything is perfect. No, we are in the real world and we have cars with human drivers. This is this H for human, and there's another human driver. And you know what? Those human drivers, they do not behave in a logic way. They are emotional, sometimes they do something that are not supposed to do while they're driving or whatever. So we have a level of uncertainty in our system that we have to deal with. But we have also some other beautiful thing that develops, because those agents, if they can communicate, they might decide, for us it is most efficient to travel together in a group, as a group of AI agents with a clear command structure. Because this is so much more efficient, yeah? And maybe they can go at higher speed, or maybe they watch out. Every car looks maybe in a different direction. So let's have a look how we can implement this idea. Of course, this is our agent that we go with and we will use here, because this is now dividing the complexity here for this fast-moving dynamic group of cars into simpler complexity group that the agents can take care of. So let's have a look at this. And you might say, yeah, the new idea is that now each module of our 5 modules performs now a specialized function, no? Enable the system to scale efficiently as the number of the agents or the complexity of the traffic scenario increases. And by separating here this in perception, collaboration, reasoning, and execution, the system can handle more complex tasks in a more structured and in a modular fashion. Or you might say, hey, the new idea is the integration of a rule-based model in the execution model to ensure that the system maintains safe and a predictable behavior, even if the high-level decisions are made by the vision language model or by the large language models, because those decisions are less precise if we have a numerical decision to make to accelerate the car or brake. So you might say the new idea is, hey, wait a minute, because we have now an optimizing of a mixed autonomy traffic that is happening, because we have humans in the loop, some human drivers that maybe go crazy on the highway, and we have to take care about them. So, and we have this collaboration module. So agents or the car do not operate anymore in isolation in an egocentric view, but now we have to optimize a system of 5 or 7 or 10 or 20 cars in total in their system interaction with the environment. So the complexity decision-making might get a step up. So you see, there are beautiful new ideas. So let's have a look at this. And the authors of the studies show us here the ideas here in a very simple visualization that I have here. So suddenly those 4 cars are not egocentric and they go alone, but they go as a group together. Now the idea is here, for example, you have now either the possibility to go as a swarm intelligence, but it is much more efficient that we have, for example, a leader. The first car says, hey, I'm on the road and I have experience for, 5 years, 100,000 miles. I have so many possible configurations. What could go wrong on a highway in my database? I don't know exactly what to do. So I will be your leader and I will guide you through here the problems we will encounter in the traffic. So he has, whatever this car is, a full sensor array. So beautiful. Looks ahead, on the side, and whatever. And then we have a role. And the role of a follower means you are just the next in the chain of this group. And you just can, your only task is more or less to follow here the leader at a specific velocity and a specific distance. But that is all more or less, because the leader will decide when the group should take actions. Now the leader has to know what is the maximum velocity this car can go, or what is the maximum velocity of the red car, or maybe here of this, whatever this car is. So the leader has to have the information of the performance of each of the group member and then decides here to the beneficial for the group. And then at the end, maybe we have also, if you want a lookout, a wingman, or is it called an assistant? And I also have here a full sensor array looking back on the side. If you want, for example, have a lane change, how to do this? Is it safe? Now there are many ways you can do this. Either the leader starts and then slowly each other car follows, or all 4 cars could do it here at the same time if there's no obstacle on the other lane. You see, there are a lot of possibilities if you have here, and if you want, intelligent autonomous group. And with this simple command structure of a leader and following. If you have 15 followers, they just follow the next one. So it is kind of a swarm in the middle of the group. I think this is an interesting algorithm to code. Now, of course, if, for example, we have a merging of two highways or of two lanes or whatever, if we have autonomous groups, another group and another group, and suddenly they come together, and we have isolated humans that are not communicating with other humans, I think it is interesting because I personally think they will form now a supergroup. Those three groups will merge in a supergroup. And if they have the same destination, hey, we have to travel on this highway together for the next, 50 or 70 miles. Yeah, let's form a group and let's just go maximum velocity, full power. So you see, then we have those isolated single human cars that are just more or less roadblocks, have a high uncertainty in their behavior for the logic semi-autonomous group that are happening now. So I think it's a highly interesting configuration, and that you can apply now a multi-agent logic on this, where each and every car has a little, if you want, AI intelligence internally. That sounds funny. So also the memory module, remember, enhances the adaptability of the agent by storing here the past experiences. The cars can also share the experiences. If there's a car brand new, so the first 100 miles on the road, it can connect maybe to another car that is only there since 2 years on this particular local route here, and it can learn here, transform here, and learn here from the other car all the previous traffic scenarios to continuously improve here the decision-making process and communicate with the other cars. So this leads to a more intelligent behavior as a group over time. And this is now in stark contrast to the unpredictable environments involving now the human drivers. So I see in the future, in the next 10, 20 years, we will see some very interesting dynamics on our highways. Yeah, I was talking about we have now not only everything in AI, and I think this is the beauty of the study, because they say, hey, LLMs are not good enough for numerical calculations. We have to give this off to a specific tool because we know how to handle this. We have experience, and this is the IDM. And this is now the intelligent driver model. And here the mathematical core is simple. You have a mechanic problem, no, in physics. So you have a dynamic of the vehicles, you have acceleration, deceleration, the speed, the distance to the vehicle ahead, you have your simple acceleration formula, whatever. So you can calculate for every second or tenth of a second here the exact parameter for each and every car in your group and in your environment that you as a group enter or leave or whatever are into. So the computational complexity of this IDM, of this intelligent driver model, has a simple time complexity, a little bit more complex collaboration decision complexity if you add here a layer of an inter-agent communication, but you have a command structure. So you see, this would be interesting to extend this research to a pure swarm structure. But then I would say we have no real-time decision-making anymore. So there are a lot of very interesting questions, and the study left me with more questions than answers. But I love those if it makes you think about this. Yeah, the interpretation here of the mathematical first term and the second term was done here simply by an AI system because, hey, this is simply mechanics. So what we have now, and I think this is also the beauty, a real AI system with a rule-based intelligence. The authors understand clearly, AI cannot do everything. AI is not everything to everybody. To have here the low-level controls of the car, when the car must accelerate, when the car must brake, when the car must take actions, it cannot go to the LLM, and the LLM might decide, hallucinating, hey, wait a second, I start now to write a French poem, and then I will take care about the control of the cars. No way. So there they decided, hey, we have to go with a system that we know. We go with rule-based intelligence. hey, if the distance to the car in front of us suddenly decreases, we don't go to the AI and say, hey, hello, yeah, how are you? A nice day today. What do you think about the situation? No. Then an action immediately takes place. Rule-based intelligence. And I think finally this is happening, that not everything is stuffed into the AI and everybody hopes the AI will take care about this. So what we have a high-level collaborative strategy that is generated by the AI, by the LLM, that is doing the causal reasoning, that applying here the logic for the dynamic of this group. But we have here actionable control commands with precision. If it is about here to take control of the car, we have a rule-based system like IDM. The benefit of this is that this reduces here also the computational load of the LLM, because we have a second system that really takes care here about the immediate real-time command structure: brake, accelerate, go to the left, go to the right, whatever. So you see, this is here the original study by Arizona State University and Salesforce, interesting partnership. And they have here CoMAL, Collaborative Multi-Agent Large Language Model for mixed autonomy traffic situations. So we do have human drivers on the road, as we will have for many, many years in the future, that people say, hey, I want to drive. But those human, if we have no communication with them and we have no control over their cars as a group, they have a high level of uncertainty. And this is another topic we will look in one of my next videos. If we have multi-AI systems with one, let's say, agent or human with a high level of uncertainty, how we can cope with this uncertainty. Yeah, but more about this in a later time. So this perception module, I just asked here my ChatGPT for Omni, hey, let's build here this perception model. And so in Python here, we define a class, we collect the data from the sensors, and we have here the image sensors, we have a LiDAR sensor, we have a radar sensor. Just the data comes in, we process the data, we have some algorithm to do the data processing, LiDAR, radar, whatever. So you see this is standard as we do. Then we detect the vehicles, we calculate the distances here from the LiDAR data, then we estimate the velocities from whatever we have, and then we generate a scenario description. And now, again, careful. This is now where this new idea comes in. We have not trained everything here that we have a reinforcement learning algorithm at the end for learning situation in a traffic flow where human drivers are involved, because we can't have this complexity learned in reinforcement learning. So what we do now, and this is what the authors found here as a solution, the system now generates a textual description of the current traffic scenario. And this is, at the first moment I thought, but this is crazy. Why would I now start to describe here the complete situation in a human language? But there is a beautiful reasoning behind this. So for my green grasshoppers on the right side, you see here the perception model interacts with the memory model, with the collaboration and reasoning model, and execution model. Yeah, everything is great. And then we have here the run. So the main function runs here, the perception model collects the data, processes it, and outputs here a scenario description. So you see, it can be as easy as this code sequence. Collect the data, process here the data, generate the textual description. And we have now here this module. It has a limited complexity. It knows exactly how to do this. They have exactly all the data about the radar, about the LiDAR, about all the cameras, stereo camera. It knows how to do this. You can train this subsystem really to almost perfection. So great. And then, as I told you, now they say, since we have now a human language description, hey, why not use here the intelligence of a multi-agent AI system instead of trying to train it with a reinforcement learning algorithm where the complexity in the real world, if you really are driving on a highway, what can happen to you is it's just crazy. You never thought about this as a potential case that you have to train your AI system on this. And the author, this is here now a direct quote from the study, say, why not reinforcement learning? This is our standard go-to tool. Nah? And they say, however, the human behavior in the real world settings are highly varied and unpredictable. And the road networks themselves are more complex and diverse. So this deep reinforcement learning performs well in specific and a controlled environment. If you have built your street network in your simulation and then you have the perfect environment with no different cars and no movements that are not predicted. But deep reinforcement learning struggles to generalize across different scenarios due to its reliance on large amount of specific training data, and you cannot have the complete available data that will happen to you on a highway in your training data. So, and they say, meanwhile, it's difficult to understand the decision-making process of reinforcement learning, which limits its interpretability because you have no idea why the car suddenly decides to do something, because you can see into the black box of reinforcement learning. You have no idea what the training data were if you enter a car. So they say a much better solution is we have our LLMs, our intelligent system. So in our framework, they say we transform all the data, the sensor data, the environment, information data, into a human language for our LLM. And now we use the intelligence of the LLM, which is now our key design choice in our experiment, in our research paper, instead of relying here on reinforcement learning training data that have maybe not in the training data set. And they say by leveraging now the reasoning capabilities of our LLMs, the agents can now handle a wide range of traffic scenarios where not have encountered during the training data. There is another plus, because we do not have only one agent, we have multi-agents. So this textual input allows now that our agent can share this information, all work on this piece of information, discuss maybe this, and negotiate strategies. And you can do this in a non-controlled system, you can do this in a swarm-operated system, you can do this in a hierarchical command system. It doesn't matter, but it's just that suddenly you apply the intelligence of your AI agents here to solve this unseen situation before. So, what is it? Easy. If a vehicle describes the environment as the car ahead is 10 meters away, moving at 50 kilometers an hour, this is immediately interpretable both by the humans and the LLM. And now if your car, if it's doing something, you say, hey, why are you doing this, car? The car can give you an immediate, transparent reason why it is doing something. And if the car is telling you, hey, I'm now gonna, I don't know, do something crazy, because, and it tells you what it detects, you can then, as a human, decide, okay, this is real, or wow, this is really something that is a pure hallucination. So you see, interesting here to move from reinforcement learning to the intelligence of a multi-agent system, because we have explainable, transparent decision-making. Now to the performance data and the GitHub repo that you have, the code for you. Now, we have here CoMAL, beautiful, everything that you need to know. I have here the HTTPS link for you. Everything is available for you. There it is here, an open source MIT license. And here for the performance data, I want to give you here a screenshot of the original study. And the authors say here, we conduct experiments using the latest LLMs, including GPT-4 Omni Mini and the Q172B, showcasing the ability of CoMAL across a diverse range of LLMs and demonstrating its superior performance over state-of-the-art reinforcement learning approaches in this particular mixed autonomy, AI agents, and human driver traffic scenarios. I think it's a beautiful study. I recommend you read it in detail. They have a lot of more information there for you. But the idea that you have now access to the decision making, because everything is translated now also to a human language, and you can follow more or less in real time what the input parameters of the LLM are if the LLM decides to take an action. This is now interesting. And also, finally, we have now rule-based intelligence added to our artificial intelligence for the numerical control cycles. This is great. I hope you enjoyed it. I hope you liked it. There was some new information for you, and it would be great to see you in my next video.